My name's Nick Lariviere. I'm a kernel developer at Wolfram Research, and I work primarily on various frameworks within the language, primarily date and time, also our quantity framework, and also as part of our client-side management for entity and the Wolfram knowledge base. I do a lot of audit-end projects also, but I primarily focus on those core frameworks and data structures in the language. Today, I want to give a overview of how we think about date and time within the Wolfram language, some of the new features we've added since version 10, and particularly since version 11, and the way that we're planning on expanding and fleshing out our date framework in the future. So just as a brief overview, I want to go over sort of a high-level description of how we work with dates and times within the language, and then look specifically at DateObject, which is our canonical representation of dates within the language, and then the different constituent components that now make up a date object and why we use these particular components and why they're necessary to resolve time. And then at the end, I want to talk about some upcoming features that we're working on and some other things that we're kicking around, and then get feedback if anyone has anything that they think is a priority or an interesting aspect they'd like to see explored more in the language. So, very basics. Time is one of the primary physical quantities associated with the way we experience the universe. It's an indefinite period that stretches from past, includes present and future, and is generally used to describe events or the progress of events throughout our experience. Generally, when we think about time, we think about it in concrete aspects of either dates, like today's October 18th, 2018, or as durations, so a period of 5 minutes. And when looking at these, it's sometimes nice to look at the analogy between physical space and time and the way that those different constituent components interact. So within physical space, we think about the analogy of three-dimensional space and time is not exact because we're working with a single dimension that runs from past to future, but if we think about a single instance in physical space, we think about a position. Within geodesy, we think about a geoposition. The analogy to that in time is a date. It's a specific period of time that's discrete and unique. And our Wolfram language representation of that is a date object. We have other representations, but they're generally more limited in describing time. When we think about something in physical space as a distance, the separation between two discrete objects, the analogy in time is a duration. In the Wolfram language, we represent this as a quantity. So a quantity of 5 seconds or 5 hours or 5 minutes. But when we think about the way those relate to a calendar, which is essentially a projection on a date, it's a framework for us to conceptually understand the way that dates are structured. Today being October 18th, 2018 is only meaningful within the framework of the Gregorian calendar. It's what we're used to thinking about with dates. But because date is an infinite span in both directions, there's no real beginning of time or end of time. We essentially choose an arbitrary reference point, and then all of our conceptions within a calendar relate back to that reference point. And another aspect I want to talk about towards the end of the talk is time systems, which you can think, again, comparing to geodesy and geopositions, is like the datum. It's how we understand that this specific point was measured. So when we talk about what time is it right now, we're talking about how we understand what now is in terms of that infinite span of time, how we resolve it down to both a calendar but also to a specific moment. And that becomes important when we do things like accounting for leap seconds and differences between different time measures. So our primary representation of dates within the language is DateObject. It is an expression that acts both as a constructor and as a container. In terms of being a constructor, if we take a DateObject, it will give you the current instant in time if you don't specify any other arguments. So if I evaluate DateObject, it will give me this current moment, Thursday, October 18th, 2018 at 1:04. And will include a time zone and other parameters that are needed to resolve that date to a specific moment. We use this to generate the specific dates that we're looking at, and we can take any number of potential arguments. So historically, Mathematica has supported strings as representations of time, lists as representations of time, and numeric values as representations of time, all with their own implicit reference framework. And DateObject knows how to take these and construct a canonicalized expression for us to use in the language. Data objects can also be used to construct from other data objects. So we can take, for example, a data object that represents a specific moment in time and effectively mod it down to a granular data object, which represents a day without the resolution going down to a specific instant. Data objects also represent containers in the language in that once we've constructed a data object, we use the same expression to carry that information around, but the container form of data object doesn't necessarily carry around options, it carries around arguments. So a data object has a date representation, a granularity, a reference calendar, and a time zone. And from this container, there are any number of properties we can extract. Some of them relate to the string representation of the date, some of them refer to specific elements like the time zone. We can use that container information to determine things like, is the year that it's contained in a leap year, etc. If we break down a little further, the way that data object is actually structured is divided into 4 parts. And those constituent elements are the date part, or the representation we use to describe the specific moment in time, the granularity, which describes the calendar granularity or calendar step associated with that date, the calendar type, which is important for referencing both the date part and the granularity, and the time zone. And all 4 of those are necessary to describe a unique moment in time. And one of the quirks of having data object be both a constructor and container is that the head itself may represent a valid data object, or it may represent something that happens to have date object. So we include this predicate of data object Q that looks at any given expression, lets you know if it actually is a data object. So for example, something that could be interpreted as a data object but hasn't been yet is not data object Q. So when we look at the representation of a date within data object, what we're looking at is the way that the specific calendar we're using chooses to categorize time. So if we look at the first argument of a canonically generated data object, it is essentially the same thing as a date list. We separate the fields out into year, month, day, hour, minute, and second. And those values correspond to important elements associated with a calendar. But we don't necessarily always need to use a list to describe these. So for example, we have a calendar that we're introducing which uses a strictly numeric value to represent time, because we're referencing an absolute time calendar which has its own implicit rules and doesn't need a list representation. It's defined fundamentally in the number of seconds that have elapsed since January 1st, 1900. We have a number of different representations of dates within the Wolfram language. Any of these potentially could be used as a first argument for data object, provided the calendar understands them. We generally use date lists as our historical reference point where we break things into 6 elements, but there are many calendars that wouldn't necessarily use 6 elements or may not want to use a list at all. So absolute time is a numeric value, so is Julian date and Unix time, and they all implicitly refer to different unit steps from a time epoch. But with date object, we can actually carry that information around, and we don't need to know that this number was a Unix time that was generated by this Unix function. I need to assume that it's based on this value. We could actually carry that along with the data object, and we don't necessarily need to pull everything back to being in its list form. Sidereal time I've included on here is not exactly the same sort of representation of a date, because sidereal time is on essentially a 24-hour clock, but it's another representation that uses quantities in this form to represent the progression of time throughout the day by looking at the not ephemeris time, but essentially looking at your position on the globe and the way that the right ascension and declination combine to give you a apparent time associated with the rotation of the Earth. So the big thing that we've added since version 10 and early on in version 11 is granularity. The way that we describe granularity is that it represents a calendar object associated with a given calendar. So a granular, for example, we have two different convenience constructs of now and today. They represent objects within a given period of time, but they have a different resolution or a different granularity. And in many ways, this granularity determines the way that we think about the date object and the way that we handle algebra associated with a date object. If someone asks you what your birthday is, you generally don't give them the absolute instant that you were born. There's a certain resolution associated with that factoid. And granularity gives us a way to represent any number of possible calendar steps all within a unified framework. We could potentially have a year object that exists and has its own properties, or a month object. But within a granular framework, we can both take explicit parameters within the date list. Since our Gregorian dates tend to have year, month, day, hour, minute, second, we can represent all of those, but we can also extend those granularities to cover extended periods. So for example, with Gregorian calendars as a reference, we have 16 different possible granularities. Some of them cover the same period of time. So we have two versions of millennium, one of them beginning on a year 0 increment and one beginning on year 1, depending on what your reference model is. We could generalize this to include decade or any number of things, but it allows us to take the information that's part of the calendar itself and affect the way that we handle granularity and arithmetic associated with those date objects. Because one of the characteristics of working with date objects is that they use relative calculations in terms of time. If I say, what is the date a year from now, you probably aren't looking at a specific number of ticks on a cesium atomic clock difference between now and then. You mean October 18th, 2019. And that arithmetic is fundamentally determined by the calendar you're associated with. And having these granular steps be essentially in lock with that notion gives us a lot of flexibility in the language so that we can describe things like a year, a month, with an implicit region associated with them. We know when this year starts and when this year ends, but we don't need to do all of our arithmetic pinned to those specific endpoints. We can look at it associated strictly with that calendar step and implicitly determine how we need to handle those endpoints later on in calculations. We also introduced a number of convenient structures, or convenient constructors associated with granularity. So we have current, next, and previous date, which take a granularity and optionally a reference date. So if I want to know what month it is, I can evaluate current date of month, or what year it is, current date of year. And it will give me the granular step associated with the current timestamp. So if I want next year, I can say next date of year, or I can give a reference date for previous date and say, I want to know what week was before Wednesday, April 3rd of 2013, and it will give me a granular object that is a week beginning on Monday, as our week granularities canonically do, and it will take it in reference to that original input date. This is generalized in terms of handling granularity, and we also allow day types. So for version 12, we're introducing support for day types, where weekend day references a day granular object, but it has criteria associated with it. So I want the next day that falls on a weekend, or I want the previous Wednesday, or I want the next Saturday. I can generate, same value, but Sunday. I can generate a granular object with reference to a specific criteria that's implied by that day type. You can also do convenient calculations, like if I want to know what the weekday immediately preceding Thanksgiving is, I can provide a reference date and then say the criteria is I want it to be a weekday. We also support comparisons between granular date objects. So for example, I can test either through sorting or strictly by comparison that today precedes tomorrow, or I can ask, is today the same thing as now? And equal understands that the granularity step means that now falls within the period of today, so there's not really an equivalence test that we could give a true or false to. So in this case, we give a warning message and we return unevaluated. One of the ways we can handle that is that we include containment functions, which give us a way of breaking down the relationship between different data objects. So that same evaluation before, I can look at, does now fall within today? And it does. I can also look at test to see whether the following Sunday is within this week. Is the following Monday within this week? No, it's not. And so date within queue tests for total containment, and we also have date overlaps queue, which tests for partial containment. So does the last week of October fall within October? It does not fall fully contained because part of it spans over to November. So date overlaps queue will return true, but date within queue will return false. For calendar types, we support a number of different calendar types within the language, and they all have different canonical representations. Since version 11, we've supported 6 primary calendars. Gregorian, which is generally what is implied if you don't otherwise specify a calendar type. We also support the Hebrew calendar, which is known as the Jewish calendar, the Al-Qura Islamic calendar, and 2 ISO calendars for ISO weekdays and ISO day years. So the ISO ordinal calendar, for example, provides the year you're in and the day within the year, but there's no notion of a month. And similarly, ISO week calendar provides the year, the week within the year, and the day within the week. So they have different implied granularities associated with the different arguments. We're also working on extending the framework to support additional representations that can either use numeric values, so a date object with a Julian date in it, or a date object with a Unix time in it, or in the future, split calendars, which in this example for absolute time has the number of seconds since 1900 and then partial seconds separate, which can become important in the future for things like date array, where we may want to be able to pack the specific arguments associated with it. There are additional calendars that may be useful that we're looking at adding in the future. The Japanese Gengo calendar, for example, is based on the Gregorian calendar, but instead of referring to the year 2018, you refer to the current year would be Heisei 30, so the 30th year of the current imperial dynasty within Japan. There's the Mesoameric long count calendar, which uses decimal steps of units, except for one specific unit, which is in steps of 18. But we basically have 7 days and then 16 steps of 18 days and then 5 steps of 20 of those steps, and each thing moving up an additional base of 20. There are also lunisolar calendars that look at either tropical or sidereal years and the moon phase together, which is something that becomes important when we're looking at astronomical calculations in the future, being able to model planetary bodies moving throughout the universe and around the globe. For time zones, we have 4 primary representations of time zones in the Wolfram language. We use numeric offsets from GMT. It's easy to think that time zones are broken down into 24 different hour periods across the globe. Right now, there are actually 38 different time zones because not everything's broken down by an hour. We support any numeric representation of a time zone. It doesn't necessarily need to correspond to one of those known GMT offsets. So I can say, I want a date object that has a time zone of 6.7 hours ahead of GMT. We generally look back to your $ time zone to initialize what that default numeric offset is. We also support, since version 10, time zone IDs. They're also sometimes referred to as internet time zones. And the way that we handle these is by looking up a reference point to a geographic region that defines how we transition both between daylight savings and non-daylight saving time if it's observed, but also historically how time has moved. So for example, there is no central time zone in a time zone ID. We reference America, Chicago. If you want to look at sort of the messy history of time zones throughout the United States, you can see that Indiana has had a particularly fractious relationship with time zones. Evansville has been in central time since the time zone was incepted, but Knox County has moved time zones. They've changed offsets regularly. The same thing has happened throughout part of North Dakota and part of Wisconsin. And these time zone IDs take into account the fact that if I move 60 years back in the past, I may have a different offset than I do right now. We also, for convenience, allow location entities to be specified for time zones, and we'll effectively look up what that the time zone associated with that location is. So I can say my time zone is Bismarck, and it will look up and know, okay, Bismarck is in Central Time. We also added support for time zone none recently, which allows you to generate a data object with no explicit time zone. So for example, if I generate a time zone and send it to someone in a different time zone, it will still represent the same reference point for them. A time zone of none will effectively delay the use of instantiation for that time. We still have a reference time that's generated for the representation, but we don't have an interpretation associated with when that falls on a GMT offset, unless I need to do something like date list or date string, at which point it will know what time zone it should use there. One notion that I wanted to mention briefly that we're working on that isn't immediately available is time zone notation that includes a time zone ID and an offset. This is particularly important because neither of those is completely sufficient to fully resolve all moments in time. In a couple of weeks, we're going to transition off of daylight saving time here, and we're going to have two different 2 a.m.s. So 2 a.m. to 3 a.m., and then we will reset, fall back an hour, and do 2 a.m. to 3 a.m. again. If you strictly use a time zone ID only, we don't know which of those two 2 a.m.s you're talking about. And again, in spring, when we jump forward an hour, there's an hour that doesn't exist. If we use just the ID or just the offset, we can't fully resolve down that one period of ambiguity around daylight savings time. And so in the future, we want to have time zones be able to support both of those specifications. So for that period, I could concretely nail down what 2 a.m. I'm talking about, or if I'm working with something like a time object that doesn't have a reference date, I'll be able to say, okay, this was 6 p.m. Central Time, but it was back in January, so it had a different offset than I have right now. So we can see in these tables that the difference between the GMT offset and the Chicago time start to diverge after a 2-hour difference from the onset or offset of GMT. So the last feature I want to talk about is one that is not currently in the Wolfram language, but it's something we're looking at extending, which is the notion of time systems. I mentioned at the beginning that a time system is somewhat analogous to a datum within a geoposition. It basically tells you how you measured what time it currently is. If someone asks you what time it is and you look at your watch, you're generally looking at a watch that's been synchronized with some other source. Typically, it's based off of Coordinated Universal Time, or UTC, which is an approximation of Universal Time Standard 1. And the complication here is that throughout history, we basically would look up at the sun and use that as our apparent solar time as our reference point for what time something was. The closer we were to noon, the higher the sun was, and we had a good reference point. But early on in the 20th century, we realized, oh, the Earth's orbit isn't perfectly elliptical, so there are different periods where we have a different offset. And for example, this graphic at the top shows that a full rotation of the Earth, when we're looking at the sun, we've actually overcorrected for our apparent location relative to the sun. And if we were to look at a distant point in space or use something like ephemeris time, we would have a different point on the clock. And the difference of a few microseconds is not major for many date calculations, but once we start talking about bodies moving through space, being off by a second or off by a few milliseconds can represent a very large change in distance. So we want to be able to support things like International Atomic Time, or Coordinated Universal Time, or geocentric coordinate time, the coordinate time that's used by GPS systems, which do not account for leap seconds. They don't care about the rotation of the Earth. They were synchronized with TIA back in the 1960s, and since then don't need to do any correction because they're not concerned with exactly how fast the Earth is rotating. And because the Earth is slowly slowing down, it means that we have to keep adding leap seconds in. And there are different ways we accommodate that, because even though we've redefined the fundamental definition of what a second is in terms of cycles of a cesium clock, it turns out that if you put atomic clocks on different parts of the Earth, they run at slightly different speeds because the geomagnetic forces and the gravity well of the planet Earth is not uniform. So the other systems like GPST simulates an atomic clock that follows the rotation of the Earth, but exists somewhere out in the vacuum of space and isn't affected by the Earth's geomagnetic field. It's something that we're looking at implementing in the Wolfram language, and we hope to be able to do things like map between these different coordinate systems of time so that we can handle astronomical calculations and things in the future. Additional features we're looking at are the inclusion of things like temporal logic, which is a modal logic operator related to time, being able to say things like, I am hungry and I will be hungry until I eat, so eventually I will not be hungry anymore. Date intervals are a concept of relating extended periods of time, but still representing discrete moments. So I can represent the time between now and 2 weeks from now. Recurring dates are useful in scheduling notation and give us a way of representing things like recurring holidays. And date arrays are something that we're also pretty excited about, being able to efficiently represent a large collection of dates and ideally be able to pack them as well. So if I have 3 million timestamps and I want to combine them down into a single object that can carry them around, it'd give us the ability to manipulate and keep that relatively small, but also be able to perform arithmetic on it without having to unpack everything and shift things around. So it looks like I'm running out of time here, but if anyone has any questions.